SF 5.2, increasing and decreasing intervals. So what I hope to do in this video is look at these derivatives of the function and figure out whether graph is increasing or decreasing, or the graph is flat. Okay, so let's talk about the slopes first. So as you remember from studying linear functions, any increasing function has the positive slope, any decreasing slope has negative slopes, and the flat or horizontal lines has the slope equals 0. So when we had linear functions, those are the constant slopes, but the same theory applies to the gradient functions. And due to this, we can have the curves that switch between increasing and decreasing. So means when we have derivatives greater than 0, we have a graph increasing. When you have a derivative less than 0, we have a graph decreasing. So when we have graph equals to 0, we have graph that is flat. Okay. So for example, we are looking at cases like if we have graph like this, we are trying to figure out whether this graph is increasing or decreasing by analytically analyzing using the differentiated values. We can use this method to access whether functions are increasing or decreasing, or which sections or the graph are the increasing or decreasing. However, finding the derivative of a function that is equal to 0 can tell you when the graph is flat, which actually can tell you where the maximum or minimum is located. And we're going to discuss this further in SF 5.8. So when you look at the example number 1, we have f of x equals to e to the power 2x, and you have to figure out whether increasing or decreasing function or both, right? So we know that this exponential function actually might has graph that looks like this, right? We can say this is the f of x equals e to the power of x. So we already know that this is kind of increasing, but we want to know whether it's increasing or decreasing or both. So we first have to differentiate this function. So we are using, from SF 5.6, we're using e to the power of nx, same as n times e to the power of nx, right? This is differentiator, so we're using this. So f prime x is same as 2 times e to the power of 2x. No matter what kind of x value we substitute, this will be a positive value. So we can conclude that this is a increasing function. Example number 2, it is asking us at what interval does the f of x equals to x squared minus 4x plus 2 is increasing. So we know that function f of x equals to x squared minus 4x plus 2. When we differentiate this becomes 2x minus 4. Okay. Since we want to figure out whether it's increasing, at which point it is increasing, we're going to set this f prime x equals 2x minus 4 greater than 0. Then we solve for the x. X is greater than 2. So we know that when x value is greater than 2, the graph is increasing. Then at the example number 3, it is asking when is the g of x equals cosine x decreasing for the intervals where x value is greater than 0 or less than 2 pi, okay, or less than equal to 2 pi. So we know that function g of x is equal to cosine x. Then we need to find the g prime x, right? When you differentiate to cosine x, it becomes negative sine x. Then since this needs to be decreasing, we can set that g prime of x equals negative sine x as less than 0. Then solving sine x, then we can solve for the sine x, and sine x is greater than 0. Then we can say that since the When sine x value is greater than 0, the graph is decreasing. So according to unit circle, we know that at the first and second quadrant, your sine x, our sine x values are positive. Then we can say that g of x is decreasing only when x value is greater than 0 and less than or equal to pi.